Welcome to the Deep Dive, where we sift through stacks of information to bring you the most compelling insights, helping you get informed fast. Today we're embarking on a broad, yet foundational, deep dive into the truly intricate and endlessly fascinating world of organic chemistry. Think of this as your exclusive, guided tour through the essential building blocks, the unique personalities, and, well, the powerful analytical tools used to understand the molecules that literally make up life itself and really everything around us. Our source material for this adventure is a comprehensive organic chemistry textbook, just packed with details on structure, bonding, reactions, analysis. It's a big journey, but don't worry, we've extracted the most crucial aha moments and woven them together for you.
Yeah, and what's truly fascinating here is how profoundly interconnected everything in organic chemistry really is. I mean, from the smallest electron interaction all the way up to the grand architecture of complex biomolecules, it's all part of one cohesive story. We'll start by exploring the very essence of what makes carbon so special, then sort of navigate through the distinctive personalities that different molecular groups, functional groups impart. Following that, we'll delve into how these molecules transform through chemical reactions. And then finally, we'll explore the sophisticated ways scientists actually see these invisible structures.
Right.
And this raises a pretty important question. How do we quickly grasp the immense breadth and depth of organic chemistry without getting completely bogged down in every single detail? Our goal today is to highlight the big ideas, the underlying logic, and the practical applications, giving you a really solid framework for understanding this core scientific discipline and hopefully truly appreciating its real-world impact.
Okay, let's unpack this right from the start. What exactly is so special about carbon that an entire massive branch of chemistry is devoted to it? I mean, really, out of all the elements on the periodic table, why carbon?
Well, it boils down to its unique bonding abilities.
Yeah, our source text highlights carbon's incredible, almost unparalleled ability to form strong, stable, covalent bonds, not just with itself, but also with a remarkably wide variety of other elements. Things like hydrogen, oxygen, nitrogen, sulfur, the halogens.
Exactly.
And this versatility lets it create this almost endless array of molecular architectures. Long chains, intricate branch structures, stable rings.
That capacity for self-linking, what chemists call catenation, that's huge. Plus, its ability to form multiple bonds, single, double, and triple, really sets it apart.
So this structural diversity, this inherent capacity to build such intricate and varied molecular architectures, is quite literally the fundamental basis for all life on Earth. It forms the complex organic compounds that serve crucial structural, chemical, genetic functions, basically everything inside every living organism.
It's the cornerstone, absolutely. If you connect this to the bigger picture, it's precisely carbon's unique combination of, well, small size, intermediate electronegativity, and its ability to form 4 strong covalent bonds that allows for such immense molecular complexity.
Intermediate electronegativity, meaning it doesn't pull electrons too strongly or too weakly.
Exactly. It's not like oxygen or fluorine, which pull electrons so hard they tend to form fewer, very polar bonds. And it's not like metals, which tend to just give up electrons. Carbon's in that just right sweet spot, allowing it to share electrons relatively equally, forming stable covalent bonds with all sorts of different elements.
Interesting. And historically, the term organic itself originally meant derived from living organisms, right? There was that old idea.
The old, almost mystical belief in a vital force, some kind of non-physical essence needed to create these natural products. Organic chemistry was initially the study of compounds with this vital force, contrasting with inorganic chemistry, which was, gases, rocks, minerals.
Until Wohler synthesized urea.
Precisely. That was the turning point in 1828. Friedrich Wöhler synthesized urea, a known organic compound, from inorganic ammonium cyanate. That groundbreaking experiment just proved a vital force wasn't required and basically opened the floodgates for chemists to start making countless organic compounds in the lab.
That historical pivot really underscores the shift from mysticism to modern science. Now, this versatility isn't just theoretical. We see it manifest in everything from the simplest organic molecule, methane, just 1 carbon, 4 hydrogens, to incredibly intricate and diverse compounds, all built on carbon's structural talent. For instance, think about tetrodotoxin.
Oh yeah, the pufferfish toxin.
Well, blue-ringed octopus venom too, apparently. It's that incredibly potent neurotoxin that blocks sodium channels.
Nasty stuff.
Our vitamin C, essential radical inhibitor, prevents scurvy, key for the immune system. Then there's carmine, that vibrant red dye from cochineal insects.
Used in food colorings, cosmetics.
Right. And of course, morphine, the powerful pain reliever from opium poppies, a cornerstone of modern medicine. All these incredibly different molecules, vastly different properties and functions, all built on the same fundamental principle, carbon's ability to form complex structures.
So, okay, to really understand how these incredible molecules are put together at the most basic level, we need to talk about the tiny elusive electrons that actually form these bonds. We often simplify electrons as tiny particles orbiting a nucleus, but here's where it gets really interesting and maybe a bit mind-bending. They actually behave like waves.
Quantum mechanics comes into play.
Yeah, our source explains that electrons in atoms and molecules aren't just following neat, predictable paths. Their behavior is described by quantum mechanics. They reside in specific regions of space called orbitals. And these aren't physical paths like planets orbiting a sun, but rather mathematical descriptions, wave functions, that chemists use to explain and predict atomic and molecular properties.
And it's tied directly to the Heisenberg uncertainty principle. Right. Which states we can't simultaneously know an electron's exact position and momentum. So instead, we talk about electron density, which is just the probability of finding an electron in a particular region of space around the nucleus. It's a probabilistic map, not a fixed location.
And these orbitals, their shapes aren't just abstract concepts, they directly dictate how atoms bond and the resulting molecular geometry. Take the 1s orbital, the lowest energy one, it's spherically symmetrical. Highest electron density right at the nucleus, decreasing exponentially as you move out. Its shape means it could bond equally in all directions, though in practice it's usually involved in core electrons, not the valence bonding in most organic stuff.
But the p orbitals are different.
Very different. The 2p orbitals are dumbbell-shaped, and there are 3 of them, oriented along the x, y, and z axes. And crucially, each 2p orbital has a nodal plane, a region right through the nucleus where the probability of finding the electron is 0. The directional nature of these p orbitals is absolutely critical for determining the specific angles and geometries when carbon forms multiple bonds.
Okay, so these orbital concepts translate directly into actual molecular structures and dictate their reactivity. How does this play out in the bonds themselves?
Well, the fundamental idea of bonding in organic chemistry revolves around sharing electrons to achieve stability, usually following the octet rule for those second-row elements. We visualize these shared electrons using Lewis structures. Take methane, CH4, carbons in the center, surrounded by 8 valence electrons, forming 4 single bonds with hydrogens, each hydrogen getting its stable duet, shows carbon aiming for that stable configuration. Or look at ethane, C2H6. There you see carbon's crucial ability to form strong carbon single bonds, which allows for building chains.
And there's a key rule here, right, about the second row elements.
Yes, a very important problem-solving hint from the text, something students often trip up on. Second row elements, think boron, carbon, nitrogen, oxygen, fluorine. They absolutely cannot exceed 8 electrons in their valence shells. This octet rule is a critical constraint for drawing valid Lewis structures and understanding stability for these key elements. Bigger elements further down the table can sometimes accommodate more, but for C, N, O, F, stick to the octet rule. It's fundamental.
Got it. So if electrons and their sharing define the bonds and their arrangement in these orbitals, how do these bonds then influence the overall shape and behavior of the molecules in three-dimensional space? Because not all bonds are created equal. Some, as the source explains, are polar.
Right. Big difference in behavior.
A nonpolar covalent bond is one where electrons are shared pretty much equally between 2 atoms, like an H2 or the CC bond in ethane. But in most bonds between 2 different elements, especially if there's a difference in electronegativity, well, the bonding electrons are attracted more strongly to one nucleus.
Which creates the polar covalent bond.
Exactly. Electrons are unequally shared, leading to a slight buildup of partial positive charge delta plus and partial negative charge delta minus at opposite ends of the bond. The classic example is the carbon-chlorine bond in chloromethane, CH3Cl. Chlorine is way more electronegative than carbon, so it pulls electron density towards itself, getting a partial negative charge, leaving carbon partially positive.
And we quantify that polarity with the dipole moment move. It's basically the partial charge times the bond length. And we draw that little crossed arrow pointing from the positive end to the negative end.
And this idea scales up from individual bonds to the whole molecule.
It does. It's important to remember that molecules themselves can have overall molecular dipole moments, which are essentially the vector sum of all their individual bond dipoles.
Yeah.
Carbon tetrachloride, CCl4, is a great example. Each CCl bond is superpolar, but because it's perfectly tetrahedral, the 4 bond dipoles point in directions that perfectly cancel each other out. Result, 0 net molecular dipole moments.
Even though the bonds themselves are polar.
Right. Geometry matters. Now, compare that to chloromethane, CH3Cl. Also to tetrahedral, but only one polar CCl bond and three slightly polar CH bonds. The CCl dipole dominates, and you get a net molecular dipole moment. But here's a tricky one. Chloroform, CHCl3, with three polar CCl bonds, actually has a smaller overall molecular dipole moment than chloromethane.
Wait, why? More polar bonds should mean more dipole, shouldn't it?
You'd think so, but again, geometry. The three CCl bond dipoles are pointing generally downwards in the tetrahedron, but they also have components pointing slightly towards each other, partially canceling themselves out. It leads to less net dipole than a single strong CCl dipole without those opposing forces. It's subtle, but important.
Okay, connecting this to the bigger picture then. This polarity, combined with the molecule's 3D shape or geometry, that directly influences everything from intermolecular forces to how molecules recognize each other in biological systems. And that geometry is largely set by hybridization.
Precisely. Carbon atoms in organic compounds don't just use their RAWs and p orbitals for bonding. They often mix them, or hybridize them, to form new hybrid orbitals that are optimally shaped and oriented for bonding.
Creating specific geometries.
Exactly. It explains the very specific shapes carbon adopts. In methane, CH4, with four single bonds, the carbon is sp3 hybridized. One O's orbital mixes with three p orbitals to form four identical sp3 hybrid orbitals. These naturally arrange themselves in a perfect tetrahedron to minimize repulsion, giving those characteristic 109.5-degree bond angles. Super stable.
And for double bonds.
Introduce a double bond, like in ethylene, C2H4. Now the carbons are sp2 hybridized. One O's mixes with two p orbitals, creating three sp2 hybrid orbitals. These lie flat in a plane, forming 120-degree angles. The remaining unhybridized p orbital on each carbon overlaps sideways to form the pi bond, the second part of the double bond. That's why ethylene is planar.
And triple bonds. Linear.
You got it. Acetylene, C2H2, with its triple bond. The carbons are spa hybridized. One S mixes with one p orbital, forming two linear spa hybrid orbitals that point 180 degrees apart. The two remaining unhybridized p orbitals on each carbon form the two pi bonds of the triple bond. These distinct shapes aren't just theoretical. They profoundly affect how molecules pack together, fit into enzyme active sites, everything.
Okay, here's where it gets really interesting for me. How do these tiny charges, these specific shapes and the way electrons are shared or unshared, how does that affect how molecules actually interact in the real world, influencing things like how they dissolve, their boiling points?
It all comes down to intermolecular forces, the attractions between molecules.
Right, these forces are absolutely fundamental. They're like the unseen hands dictating a compound's physical properties, boiling point, melting point, and critically, how well it dissolves in different solvents. Let's start with hydrogen bonding.
Often the strongest intermolecular force we deal with in organic chemistry.
Yeah, it occurs between an electrophilic hydrogen, basically one bonded to a very electronegative atom like oxygen and OH, or nitrogen and NH, and the lone pair electrons on another nearby oxygen or nitrogen atom. But our source makes a key point. Even though it's strong compared to other intermolecular forces, it's still way, way weaker than an actual covalent bond.
Yeah.
Like 20 kilojmol to break an H bond versus maybe 400 kilojmol to break a covalent OH bond.
A huge difference, and that difference has dramatic observable effects. Take ethanol, C2H5OH. It has that OH group, so it can form lots of hydrogen bonds with other ethanol molecules. Boiling point. 78 degrees Ctex. Now compare it to dimethyl ether, CH3OCH3, same molecular formula, C2H6O, but it's an ether, no OH group. It can't hydrogen bond with itself. Its boiling point is minus 24 degrees.
Wow, over 100 degrees difference just from that one type of bond.
Exactly, all due to hydrogen bonding. You see the same thing with the amines. Trimethylamine and CH3,3, no NH bonds, boils at 3 degrees C. Ethylmethylamine with 1 NH boils at 37 degrees C. Propylamine with 2 NH bonds boils higher still at 49 degrees C. More NH bonds mean more hydrogen bonding, higher boiling point. It's a clear trend.
Okay, so beyond hydrogen bonding, we also have van der Waals attractions. These are weaker, right?
Generally weaker, yes. They're transient forces that exist between all molecules, even completely nonpolar ones. They happen because electrons are always moving, creating temporary fluctuating dipoles that induce dipoles in neighboring molecules. They're especially important for nonpolar molecules, or the nonpolar parts of larger molecules. And the source gives a useful hint. These forces increase with molecular weight and, importantly, with surface area.
Surface area.
Yeah, think about it. Two flat, long molecules can have more points of contact for these weak attractions than two compact spherical molecules of the same weight. So a long, straight-chain alkane will generally have a higher boiling point than a highly branched isomer with the same number of carbons, because it has more surface area for these van der Waals interactions.
That makes sense. So these subtle forces really dictate everyday phenomena. Boiling points are a direct consequence. Stronger intermolecular forces mean you need more energy, higher temperature to separate the molecules into gas.
Absolutely. The source has tables showing this clearly, comparing compounds with and without hydrogen bonding. It even shows how boiling points of alkyl halides increase as you go down the halogens, F, Cl, Bri, partly because the larger halogen atoms increase the molecule size and surface area, boosting those van der Waals forces.
And there's solubility. The classic rule is dissolves like.
Which isn't just a catchy phrase. It's rooted in the thermodynamics of intermolecular forces. Polar solutes, like table salt, NaCl, dissolve well in polar solvents like water. Why? Because the water molecules, with their strong dipoles and ability to hydrogen bond, can surround and stabilize the individual Na+ and Cl ions. That's solvation. This strong solvation, plus the increase in randomness entropy when the crystal breaks apart, overcomes the energy needed to break the ionic lattice. Try dissolving salt in gasoline, nonpolar. Doesn't work. The gasoline can't solvate the ions effectively.
And the reverse is true for nonpolar stuff.
Exactly. Nonpolar things, like paraffin wax, long alkanes, dissolve well in nonpolar solvents like gasoline or hexane. Here, the weak van der Waals attractions between wax molecules are easily replaced by similar weak attractions with the solvent molecules. There's no big energy penalty, and entropy increases as they mix. It's favorable.
Alcohols are interesting here, having both polar and nonpolar parts.
Right, they're a great example of the balance. The OH group is polar, hydrophilic, water-loving, loves hydrogen bonding with water. But the alkyl chain, the carbon part, is nonpolar, hydrophobic, water-hating. So small alcohols like methanol and ethanol mix perfectly with water, but as that carbon chain gets longer, the hydrophobic part starts to dominate and water solubility drops off sharply. The textbook suggests a rough rule of thumb. One OH group can sort of carry about 4 carbon atoms into water solubility. More carbons than that, and it becomes mostly insoluble.
Interesting. And you mentioned phenol being unusually soluble.
Yeah, phenol, C6H5OH, an aromatic alcohol, is more soluble in water than a typical 6-carbon straight-chain alcohol, partly due to its relatively compact shape and its ability to form particularly strong hydrogen bonds with water. Shows how subtle structural features can influence these properties.
Okay, this really sets the stage. How do these fundamental properties and forces then manifest themselves in the incredible diversity of organic compounds we see, giving them their unique characteristics, their personalities? All right, now we move from the basic building blocks and the forces between them to the truly distinctive personalities of molecules, their functional groups. These aren't just random collections of atoms. They're specific groupings that act as the centers of chemical reactivity. They dictate how a molecule behaves, how it reacts, what its overall character will be.
Exactly. Recognizing functional groups is absolutely the first step to predicting reactivity, physical properties, even biological activity. It's like learning the key character types in chemistry. Let's take a quick tour.
Okay, where do we start? Maybe with the simplest ones. Hydrocarbons.
Good starting point. The hydrocarbon frameworks. Just carbon and hydrogen. Alkanes. The paraffins, think methane, ethane, propane, butane. They only have single CC and CH bonds, so they're saturated. Their personality. Pretty inert, not very reactive. Mostly structural backbones or fuels. Natural gas is mostly methane, ethane, propane. Gasoline is a mix of branched alkanes like pentane, hexane, octane isomers, chosen for volatility.
Okay, so alkenes are pretty stable. What about alkenes?
Alkenes. Now we introduce a CQC double bond that makes them unsaturated. That double bond is a region of high electron density, making them much more reactive than alkenes. Their personality is eager to react. They love addition reactions, adding atoms across the double bond. Ethylene or ethene is a huge industrial chemical. Used to make polyethylene plastic, ethanol, vinyl chloride for PVC, tons of stuff. It's also a plant hormone involved in fruit ripening.
And alkanes, triple bonds.
Alkenes contain a C triple bond, even more unsaturated, even more reactive, especially towards addition. Acetylene, or ethene, is the classic example. Colorless gas, but mix it with oxygen. You get an incredibly hot flame used for welding and cutting. Their personality is intense, highly reactive.
All right, beyond just carbon and hydrogen, halogens.
Alkyl deaths.
Yeah.
General formula Rx, where X is a halogen, FClBri, bonded to a carbon. The halogen is electronegative, making the carbon slightly positive, electrophilic, and the halogen itself can often leave easily. It's a good leaving group. Their personality is one of exchange and departure. They're key intermediates in making other functional groups. Applications. Some are anesthetics, like isoflurane. Historically, DDT was a potent insecticide, though banned now due to environmental issues.
Okay, now the big ones. Oxygen-containing groups. These seem really diverse.
They are. Oxygen's electronegativity and ability to H-bond make for a lot of variety. Alcohols, ROH. That hydroxy group makes them highly polar, capable of strong hydrogen bonding. This hugely impacts boiling points and solubility. They can act as weak acids or weak bases and good nucleophiles. Personality, versatile. Methanol, wood alcohol, is a solvent and fuel. Ethanol, grain alcohol in drinks, cosmetics. Isopropyl alcohol is rubbing alcohol.
And ethers.
Like ROR, still polar because of the oxygen, but crucially, no OH bonds, so they cannot hydrogen bond with themselves. Their boiling points are much lower than comparable alcohols. However, the oxygen's lone pairs can accept hydrogen bonds from other molecules like water. Personality. Generally less reactive than alcohols, often used as solvents. Diethyl ether was the famous early anesthetic, also used in starting fluid.
Then the carbonyls. CO. Ketones and aldehydes.
Carbonyl compounds. Ketones RCOR and aldehydes RCOH. That CO double bond is key. Oxygen is highly electronegative, pulls electron density away from the carbon, making the carbonyl carbon electrophilic, meaning it attracts electron-rich nucleophiles. Personality. Reactive center, often responsible for smells and tastes. Acetone, a ketone, is nail polish remover, a common solvent. Benzaldehyde, an aldehyde, gives almond extract its smell. Corvone, a ketone, is spearmint flavor.
Lots of flavors and smells from carbonyls. Finally, nitrogen. Amines.
Amines. Think of them as derivatives of ammonia, NH3. They're basic because of the lone pair of electrons on the nitrogen atom. Primary RNH2 and secondary RD2NH amines have NH bonds, so they are polar and can hydrogen bond, though usually weaker than OH bonds. Tertiary amines, R3N, have no NH bonds. Personality, basic and nucleophilic, super important in biology, amino acids, neurotransmitters, and in pharmaceuticals.
Wow, so even subtle changes in these groups really dramatically alter a molecule's behavior.
Absolutely. It leads to this vast array of compounds with incredibly diverse applications. Fuels, drugs, plastics, flavors, you name it. And connecting this back, recognizing these functional groups is the absolute first step to predicting how a molecule will react, what it can do. It's like learning the vocabulary and grammar of organic chemistry.
Okay, so molecules have these personalities, these functional groups, but they don't just sit there. They react, they transform. These reactions aren't random, though. They follow specific pathways, driven by fundamental energy changes. Understanding the why and how is critical.
Exactly. We need to look at reactions through two main lenses: thermodynamics and kinetics.
Yeah.
Let's start with thermodynamics. This basically tells us if a reaction is energetically favorable, will it tend to happen on its own? Reactions generally favor products that are lower in energy, which we measure as enthalpy, or PNEH, and products that have more randomness or disorder, measured as entropy.
And these are combined in the Gibbs free energy.
Right, the equation AHE degrees AH degrees, where T is temperature. If AHE degrees is negative, the reaction is spontaneous or exergonic favorable. If it's positive, it's non-spontaneous or endergonic. Now, for many organic reactions, especially those non-involving gases or big changes in molecule numbers, the enthalpy change, AH degrees, is often the dominant factor. So AG degrees is often approximated by AH degrees.
And enthalpy relates to bond breaking and forming.
Precisely. A key point to remember. Breaking a bond always costs energy, endothermic. Forming a bond always releases energy, exothermic. The overall AH degrees for a reaction is the balance energy put in to break bonds minus energy released when new bonds form. If more energy is released than put in, the reaction is exothermic, favorable AH degree.
Okay, so thermodynamics tells us if a reaction can happen, but not how fast. That's kinetics.
Exactly. Kinetics is all about the rate of the reaction. How fast does it go? The rate depends heavily on the activation energy, ELA. That's the energy barrier the molecules have to overcome to react. Think of it as a hill they need to climb. Higher activation energy means a slower reaction. Catalysts work by lowering this activation energy barrier, speeding things up without changing the overall thermodynamics, the start and end points. Reaction rate also depends on the concentrations of the reactants. We often express this with a rate law, like rate equals Kreibe-Ab, where K is the rate constant and A and B are the reaction orders, telling us how the rate changes as we change the concentration of A or B. These orders have to be determined experimentally. They reflect the reaction mechanism.
And we visualize this with reaction energy diagrams.
Yes, those diagrams are incredibly useful. They plot energy versus the reaction progress. Reactants are on one side, products on the other. The hills represent the transition states. Those are the highest energy points along the reaction pathway. A transition state is a fleeting, unstable arrangement where old bonds are partially broken and new bonds are partially forming. You can't isolate a transition state. If a reaction happens in multiple steps, there will be intermediate valors and multiple transition state peaks. The highest peak determines the overall activation energy and thus the rate.
Okay, given these energy principles, how do we start classifying the huge variety of reactions?
Yeah.
And what about those short-lived species, the reactive intermediates, that often pop up? Hashtag tag 3.2, common reaction types, and reactive intermediates. Let's dive into some core reaction types and those fleeting, highly reactive intermediates. These are really the heart of understanding how organic molecules change and how chemists build new ones. First up, substitution reactions.
Where one atom or group replaces another, very common. Two main flavors we focus on are SN1 and SN2.
All right, SN2 stands for substitution nucleophilic bimolecular. Key features.
It's a one-step concerted process. The nucleophile, something electron-rich, loves positive centers, attacks the carbon from the backside, kicking out the leaving group simultaneously. Favored by strong nucleophiles, unhindered substrates think methyl or primary carbons, where there's room for the backside attack and typically polar aprotic solvents.
And the classic SN2 feature is the inversion.
Yes, the Walden inversion or inversion of configuration. If the carbon being attacked is a chiral center, its stereochemistry gets flipped like an umbrella blowing inside out. Very characteristic.
Okay, then SN1. Substitution nucleophilic unimolecular. How's that different?
It's a two-step process. Step 1, the slow rate-determining step, is the leaving group just leaves, forming a carbocation intermediate. Step 2, the nucleophile attacks that carbocation. This is favored by weak nucleophiles, substrates that form stable carbocations, tertiary, secondary, primary, and typically pyrotic solvents that can help stabilize the leaving group and the carbocation.
And because the carbocation is flat.
Exactly. The carbocation intermediate is planar, sp2 hybridized. So the nucleophile can attack from either face, often leading to a mixture of stereoisomers, potentially a racemic mixture if a new chiral center is formed, less stereospecific than SN2.
Okay, substitution. What about elimination reactions? E1 and E2.
Elimination removes atoms or groups, usually to form a double bond with an alkene. Often competes with substitution, which can make predicting products tricky. Conditions matter. Strong base often favors elimination. E1 is unimolecular elimination. Like SN1, it's two steps, goes through a carbocation intermediate. Competes with SN1, especially with tertiary substrates and weak base-shy temperatures.
And E2.
E2 is bimolecular elimination. Like SN2, it's a one-step concerted process. Requires a strong base to pull off a proton while the leaving group leaves simultaneously. Often needs a specific geometry called antiparaplanar, the H being removed, and the leaving group need to be on opposite sides and in the same plane. Reactivity generally follows 3 degrees, 2 degrees, 1 degree alkyl halides because the transition state leads to a more substituted, more stable double bond.
Got it. Then we have addition reactions,
Right.
mostly with alkenes and alkenes.
Right. Adding things across a double or triple bond. Electrophilic addition to alkenes is a major one, and the key rule here is Markovnikov's rule.
Ah, yes, Markovnikov. The rich get richer.
Sort of. In the addition of something like HBr to an unsymmetrical alkene, the hydrogen, the electrophile, H+, adds to the carbon of the double bond that already has more hydrogens. Why? Because this forms the more stable carbocation intermediate. Tertiary is better than secondary, etc. That intermediate then gets attacked by the bromide ion.
Does it always work that way?
Mostly for electrophilic addition. Interestingly, if you do HBr addition in the presence of peroxides, it goes via a free radical mechanism and you get the opposite regiochemistry called anti-Markovnikov addition. The Brie radical adds first to the less substituted carbon. Different mechanism, different outcome.
And halogenation, like adding Br2.
That's another classic addition. Adding Br2 or Cl2 across an alkene, it goes through a special bridged intermediate, a halonium ion, like a bromonium ion. This bridged ion blocks one face, so the second halide ion has to attack from the opposite face. The result is always anti-stereochemistry. The two halogens end up on opposite sides of what used to be the double bond.
Okay, one more category. Oxidation and reduction.
These involve changes in the oxidation state of carbon. A simple way to think about it in organic chemistry. Oxidation often means adding bonds to oxygen or removing bonds to hydrogen. Reduction is the reverse, removing bonds to oxygen or adding bonds to hydrogen. For example, oxidizing a secondary alcohol, R2CHOH, gives you a ketone, R2CO. You've removed one H from the oxygen and one H from the carbon, effectively adding a COO bond. Common oxidizing agents are things like bleach, NaOCl, or chromic acid. Reduction might turn that ketone back into the secondary alcohol.
And driving many of these reactions are the reactive intermediates, these short-lived species.
Crucial players. They're fleeting, never in high concentration, but they often dictate the reaction pathway and outcome. Carbocations. Carbon with a positive charge. We mentioned them in SN1E1. They're sp2 hybridized, planar, with an empty p orbital, highly electrophilic. Stability is key. Tertiary, secondary 2 degrees, primary 1 degree methyl. Stabilized by alkyl groups through hyperconjugation electron donation from adjacent CH or CC sigma bonds into that empty p orbit.
Hyperconjugation, like a weak resonance.
Kind of, yeah. It spreads out the positive charge. Resonance itself is even better for stability if you have double bonds or lone pairs next door. Free radicals. Carbon with an unpaired electron. Also typically sp2 hybridized and planar with a single electron in the p orbital. Also stabilized by alkyl groups and resonance, similar logic to carbocations, involved in radical reactions like that anti-Markovnikov HBr addition.
And carbenes. Those sound weird.
Carbenes. They are a bit unusual. An uncharged carbon atom with only 2 bonds and 2 non-bonding electrons. Highly reactive. Can exist as singlets, electrons paired, or triplets, electrons unpaired. Used in specific reactions like adding across a double bond to make a 3-membered ring, cyclopropane.
Wow. So understanding these intermediates, their stability, how they form, how they react, is critical to predicting what products you'll get.
Absolutely. They can rearrange, they determine stereochemistry. Understanding intermediates is key to controlling reactions. They're the hidden directors of the molecular play.
Okay, we've covered bonding, functional groups, reactions. But how do chemists actually figure out the structure of a molecule they've made or isolated? We can't just look at them.
Right. We need tools to probe their structure indirectly. Spectroscopy is the answer, using different parts of the electromagnetic spectrum to get different kinds of information.
First up, infrared IR spectroscopy. You described this earlier as listening to a molecule's musical notes or vibrations.
Yeah, it's a great analogy. IR spectroscopy is fantastic for identifying the functional groups present in a molecule. It uses infrared light, which has the right energy to make molecular bonds vibrate, stretch back and forth, or bend. Different types of bonds, CO, OH, CH, CC, etc., vibrate at characteristic frequencies when they absorb IR light.
But not all vibrations absorb IR light.
Correct. For a vibration to be IR active, it must cause a change in the molecule's overall dipole moment during the vibration. That's why very polar bonds like carbonyls, CO, or hydroxyls, OH, give strong IR signals. Symmetrical nonpolar bonds like the CC in ethylene might be weak or absent.
So we look for peaks at specific frequencies, measured in wave numbers.
Exactly. The horizontal axis of an IR spectrum is usually in wave numbers, C in euro, which is proportional to frequency and energy. And certain functional groups show up in very predictable regions, acting like fingerprints. An OH stretched from an alcohol or carboxylic acid. Look for a broad, often strong pick somewhere around 3200, 3600 C in Euroman. That broadness is key. It's due to hydrogen bonding.
A dead giveaway for OH.
Totally. A CO stretch, carbonyl, usually a very strong, sharp peak. Ketones around 1710 centimole, aldehydes maybe 1725 centimole, esters 1735, 1750 centimole, carboxylic acids around 1710 centimole, often broad too, overlapping the OH. Conjugation, alternating double single bonds, lowers this frequency.
These H months.
Very useful. sp3-CH stretches, alkenes are always just below 3000 centimole. sp2-CH stretches, alkenes, aromatics, and centipre-CH stretches, alkenes are always just above 3000 centimole. So just looking at that 3000 line tells you if you have unsaturated CH bonds.
Simple but powerful. What about amines? NH.
NH stretches also show up around 3300 centimole, similar to OH, but usually sharper and weaker. A primary amine, RNH2, typically shows 2 distinct peaks, symmetric and asymmetric stretch. A secondary amine, R2NH, shows 1 peak. A tertiary amine, R3N, has no NH, so nothing there.
Okay, connecting this back, IR is great for telling us what functional groups are present, or maybe just as importantly, what's not there. If you don't see a strong peak around 1700 centimole, you probably don't have a carbonyl.
Exactly. It's usually the first piece of spectroscopic data chemists look at. Quick, non-destructive, gives you a fast overview of the key players in the molecule. Helps narrow down the possibilities immensely.
Okay, if IR spots the functional groups, what does mass spectrometry, MS, tell us? You said it's like weighing the molecule and smashing it.
That's a pretty good description. Mass spec primarily does two things. It measures the exact molecular weight of the compound, and it gives us information about its structure by looking at how it breaks apart, fragments, under high energy. It's incredibly sensitive. You can get data from tiny amounts of material, even if it's not perfectly pure.
How does it work? You ionize the molecule.
Yeah. Typically, in electron ionization, EI, mass spec, you bombard the molecules with high-energy electrons in a vacuum. This knocks out one of the molecule's own electrons, creating a positively charged species called the molecular ion, M+. It's the original molecule, just missing an electron and carrying a positive charge. The mass spectrometer measures the mass-to-charge ratio of this ion, and since the charge Z is usually +1, the Melisede value directly gives you the molecular weight.
What's that rule about nitrogen and the molecular weight?
The nitrogen rule, for compounds containing only C, H, O, sp halogens.
Hey.
If the molecular weight, the Melisede of M+, is an even number, the molecule contains an even number of nitrogen atoms, usually 0. If the molecular weight is odd, it must contain an odd number of nitrogen atoms, 1, 3, etc. That's it. Quick check.
Okay, molecular weight is useful, but the fragmentation, that tells us about structure.
Yes, the fragmentation patterns are like puzzle pieces. The molecular ion formed often has a lot of excess energy, causing it to break apart into smaller, positively charged fragment ions and neutral fragments, which aren't detected. The spectrometer detects the Millids values of all the positively charged fragments. The specific ways a molecule breaks apart are often characteristic of its structure. We look for common losses, like loss of 18 water suggests an alcohol, loss of 15 methyl group, loss of 29 ethyl group, etc.
Are there specific types of fragmentation that are really informative?
Absolutely. Alpha cleavage is a big one, especially for alcohols, ethers, and amines molecules with heteroatoms, O or N. This is where a bond next to the carbon bearing the heteroatom breaks. This cleavage is favorable because it often forms a resonance-stabilized cation. Seeing strong peaks corresponding to alpha cleavage fragments gives you good evidence for those functional groups and where they are located.
And you mentioned GCMS before, combining separation with analysis.
Right. Gas chromatography mass spectrometry, GCMS, is a powerhouse technique. The GC part first separates a mixture into its individual components based on their boiling points and interactions with the GC column. More volatile stuff comes out first. Then, as each pure component comes off the column, it goes directly into the mass spectrometer to be analyzed, giving you the molecular weight and fragmentation pattern for each component in the original mixture.
That sounds incredibly powerful for analyzing complex mixtures.
It revolutionized analytical chemistry. Think about analyzing environmental samples for pollutants, testing athletes for doping agents, identifying compounds in natural extracts. GCMS is often the go-to method. It combines the separation power of GC with the identification power of MS. And notice the connection back GC separates based on volatility, which is governed by those intermolecular forces and boiling points we discussed earlier.
Okay, IR gives functional groups, mass spec gives molecular weight and fragments. But you said nuclear magnetic resonance, NMR spectroscopy, is maybe the most powerful, like getting a molecular blueprint?
It really is. NMR gives you incredibly detailed information about the carbon-hydrogen framework of the molecule. It tells you about the different types of hydrogens and carbons, how many of each type there are, and how they are connected to each other.
How does it work? It uses magnetism.
Exactly. It relies on the fact that certain atomic nuclei, like protons, 8H, the nucleus of hydrogen, and carbon-13, a less abundant isotope of carbon, have a quantum mechanical property called spin. This makes them behave like tiny spinning magnets.
When you put a sample in a very strong external magnetic field, BH, these tiny nuclear magnets align either with the field, lower energy, or against it, higher energy.
NMR then uses radio frequency, RF waves. When the RF frequency exactly matches the energy difference between these two spin states for a specific nucleus, the nucleus absorbs the energy and flips its spin. This absorption is called resonance.
And the key is that different nuclei in the molecule resonate at slightly different frequencies.
Precisely. The exact frequency needed for resonance depends very sensitively on the local electronic environment around each nucleus. Electrons orbiting the nucleus create their own tiny magnetic fields that shield the nucleus slightly from the main external field. Different chemical environments mean different amounts of shielding, which means different resonance frequencies. This difference is what we measure as the chemical shift.
Okay, chemical shift.
Yep.
Measured in ppm relative to a standard, TMS.
Right. Tetramethylsilane, TMS, is the common reference, set to 0 ppm. The chemical shift scale typically goes from 0 to maybe 10-12 ppm for proton NMR, where a signal appears tells you about the nuclease's environment. Electronegative atoms, like ON halogens nearby, tend to pull electron density away. That's called deshielding. Deshielded nuclei feel more of the external field and resonate at higher frequencies, meaning higher chemical shift values further downfield. So protons next to an oxygen, like in an alcohol or ether, typically show up around 3 to 4 ppm, while simple alkane protons are upfield around 1-2 ppm. Aromatic protons are further downfield, 7 to 8 ppm. Aldehyde protons way downfield, 9 to 10 ppm. Carboxylic acid protons even further, 10 ppm. These characteristic ranges are super informative.
Okay, so chemical shift tells us the type of environment. What else does NMR tell us? Integration.
Yes, integration. The area under each signal, or group of signals, in a proton NMR spectrum is directly proportional to the number of protons generating that signal. So if you have one peak with an area of, say, 2 units and another with an area of 3 units, you know there's a 2.3 ratio of protons in those two different environments. This helps you figure out how many hydrogens belong to each part of the molecule.
And the splitting, that tells us about neighbors.
Exactly. Spin splitting, or multiplicity, is often the most powerful piece of information for connectivity. It arises because the magnetic field experienced by one proton is slightly affected by the spin states of protons on adjacent atoms, usually carbons. The simple n+1 rule often applies. If a proton, or group of equivalent protons, has n equivalent neighboring protons, usually on the next carbon, its signal will be split into n+1 peaks. So a proton with 0 neighbors, n0, is a singlet, 1 peak. 1 neighbor, n1, gives a doublet, 2 peaks. 2 neighbors, n2, gives a triplet, 3 peaks. 3 neighbors, n3, gives a quartet, 4 peaks, and so on.
And you learn to recognize patterns like an ethyl group.
The ethyl group, CH-Eris, is the classic example. The CH protons have 2 neighbors, the CH, so they appear as a triplet, 2 plus 1 and 3. The CH protons have 3 neighbors, the CH, so they appear as a quartet, 3 plus 1 and 4. Seeing a triplet and a quartet with the right integration, 3.2, is strong evidence for an ethyl group. The spacing between the peaks and a multiplet is called the coupling constant, J, measured in hertz. Coupled protons split each other with the same J value, which confirms they are neighbors.
What about protons on OH or NHA? They sometimes behave differently.
They do. Because they can undergo rapid chemical exchange, especially if there are traces of acid or base, their signals are often broad singlets, and they might not show clear splitting or be split by neighbors. We can identify them using the D-Tiro shake. Add a drop of deuterium oxide, heavy water, to the NMR tube. The OH or NH protons will exchange with deuterium D. Since deuterium doesn't show up in Eddy's NMR, the OH or NH signal will disappear from the spectrum, confirms it was an exchangeable proton.
And quickly, NJHE, NMR, what does that add?
It maps the carbon skeleton directly. It's less sensitive than proton NMR because dikesi is only about 1% abundant naturally, but it's incredibly useful. You typically get one sharp signal for each unique type of carbon atom in the molecule. The chemical shift range is much wider than for protons, 0 to 20 ppm, so signals are usually well separated. Standard AT-NMR spectra are usually proton decoupled, meaning the splitting by attached protons is removed, so each carbon signal appears as a simple singlet. This makes the spectrum cleaner, though you lose direct CH coupling info, which can be obtained with special techniques if needed. It tells you the number of different carbon environments.
So putting them all together, IR, mass spec, each NMR, KTC NMR, you get a complete picture.
That's the goal. Each technique provides complementary pieces of the puzzle. MS gives the molecular formula from accurate mass and fragmentation clues. IR identifies functional groups. AT-NMR maps the proton framework, connectivity, and relative numbers. AT-NMR shows the carbon types. By integrating all this data, like detectives using different kinds of evidence, chemists can confidently determine the complete structure of even complex, previously unknown molecules. It's a fascinating process of deduction. Hashtag tag outro.
Wow. Okay. We have covered a huge amount of ground today on a deep dive. I mean, from the absolute fundamentals of carbon bonds and why carbon is so special, through molecular architecture, intermolecular forces,
to the personalities of functional groups, how reactions happen.
And finally, these incredibly sophisticated instruments like IR, mass spec, and NMR that let scientists literally see molecules. We've explored how carbon's unique properties lead to this staggering diversity of compounds.
Yeah, and how those functional groups really dictate reactivity, and how chemists use these analytical tools, piecing together clues to figure out the unseen structures.
It really is a journey from the, almost abstract world of electron waves right down to identifying real, tangible compounds that impact our lives.
And connecting it to the bigger picture, all this foundational knowledge is just indispensable for anyone really digging into organic chemistry, whether you're aiming for a career in science, doing research, or honestly just curious about how the world works at a molecular level. It hammers home that point. Structure and properties are intrinsically linked. They're two sides of the same coin. Understand one, you can predict the other. It gives you this powerful, coherent framework.
So what does this all mean for you, our listener? Hopefully you now have a much stronger grasp of the core concepts that define organic chemistry. The reasons carbon is unique, the language of bonds, the forces governing interactions, the key personalities of functional groups, the ways molecules transform, and, importantly, the detective tools used to reveal their hidden structures. It's really a journey of discovery that continues to yield incredible insights into medicine, material science, environmental science. The very processes of life itself.
Absolutely.
So here's a final provocative thought for you to mull over. This constant interplay we've discussed, structure, reactivity, analysis, and organic chemistry, is really a profound testament to both nature's incredible ingenuity and our own human drive to understand it. Next time you encounter a complex organic compound, maybe it's a medication or a fuel, a plastic, a flavor, even just the smell of a flower, pause for a second. Think about the intricate dance of electrons forming its bonds, the specific 3D shape its atoms take, and the really clever ways scientists use light and magnetic fields to figure out its secrets. What other invisible complexities might be hiding right there in plain sight, just waiting for the right tool and maybe the right curious mind to reveal them?